improving in from outside. Really happy you could all be here. We're going to do a talk tonight kind of on container orchestration with Azure Kubernetes Services, also known as AKS. So I've been working with this a little bit, doing a project right now with Kubernetes on-prem, but really wanted to talk about the AKS service. A little bit about me, senior consultant at Improving. I've been with Improving in about a month, it'll be 5 years. Some of the past projects that I've done with them, WPF, desktop application development, some SSIS integration work, long-term project with BizTalk integrations in the healthcare space, some JavaScript, Angular web dev, and the current project is a microservice project with containers and Kubernetes and all that, which led me into this. Some passion projects. There's a project called Kegbot, measures beer tracking out of a kegerator. So I kind of helped one of the developers that spearheads that. And then I'm also into 3D printing. So I've got a project called Octavox out there that's an Alexa plugin for 3D printers. That's just a little bit of background about me. So real quick agenda. Let me make sure I see some chats here. Just want to make sure somebody monitors and let me know it's not like you can't hear me or anything like that.
Yeah, you're good.
Good deal. So agenda, just real quick overview of what are containers, what is containerization, what is container orchestration, what does that mean? We'll talk a little bit about Kubernetes overview, literally just scratching the surface. It's a huge topic, a lot of different details that you can get into, but we'll try to show you some examples in AKS, and then a little bit of transitioning that to how it works inside the Azure Kubernetes service, and then most of the time will be spent on the demo. So what are containers? So this diagram here on the right kind of lays out the difference between a container and a virtual machine. So containers package an application and the environment into a single immutable unit. So they contain the minimum software required to run a desired application. Small footprint, fast startup. They can be independently managed, independently deployed, independently scaled. Docker and the Docker engine are kind of the most widely known containerization technologies and engine that containers run on. They're also portable. So if you build a Docker container on a Windows OS, assuming it's a Linux container, you can move that to any type of server that has the Docker engine. And then it's just some other containers that I'll be honest, I have not touched at all. Rocket, LXC, and OpenVZ. So I have not touched any of those technologies, but those are just some different engines. And just to point out kind of the overall difference here, if you look at the virtual machine kind of architecture, you'll have your main server, the host OS, then some type of hypervisor, and then on top of that, full guest OSs. So in this example, you'd have a Windows virtual machine running on some type of hypervisor, and it has all of the binaries and libraries to run Windows, but then it maybe is only running your really small apps. So there's a lot of overhead to run the guest OS if it's just needed to run some small application. Whereas a container just has the binaries and libraries needed to run that application, and then runs on a Docker engine that then sits on top of the host OS and then physical hardware. So that's kind of the differentiator between a full virtual machine and the containerization of a platform or an application. So then once you've got these containers, what is container orchestration? So container orchestration is kind of just a way to manage all of these. These containerized solutions can consist of many, many containers, and that software manages their deployments, their life cycles, et cetera. Some of the features, they can maintain the requested number of container instances. So if I want to have a I guess, a pool of 5 containers and one of them dies, this container orchestrator will ensure that there are always 5 available and restart containers as needed. Also, we'll demo this tonight. A big piece of this is the dynamic creation of additional containers under load. So this is where you can get that dynamic scaling that Kubernetes and containerization gives you. So as your site or application comes under more traffic, you can actually spin up more instances and load balance across them to maintain that load and support that additional traffic. Again, in the same way as automatic scale up, automatic scale down. So the removal of containers once those loads return to normal level. Self-healing in the event of node failures or container failures. So if something crashes or goes down, the orchestrator can spin that back up and ensure that it's still running. Popular solutions for this, Docker Compose, Docker Swarm, and Kubernetes that we're going to be talking about here tonight. So at a high level of Kubernetes, again, just scratching the surface of all of this. So there's a control plane or a master node, and this has several components, an API server. You'll see a lot of commands tonight using the kubectl command in a command prompt. That's just interacting with the API server. Another component is a scheduler. This manages allocating the pods or these different containers. The concept of Kubernetes has the concept of a pod that is kind of an encapsulation around a container, or it can be multiple containers inside of a pod. But the scheduler is responsible for deciding what actual physical node that pod gets run on. And etcd database that has all of the information about the pods and where things are, and then the controller manager. And then you've got one or more worker nodes that run several applications. Kubelet is the agent on that node that connects this back to a Kubernetes cluster. The container runtime, in this case we'll be using Docker containers, the Docker engine, kubeproxy, which is the networking, and then obviously the containers themselves that run on the nodes. And so these kind of diagrams here, you can show here kind of what different pieces are and where they run. And this shows kind of the layout of an application that you might have a standard database set up, and then a management VM, one or more nodes, and then pods would be run on the physical or virtual machines. At a high level, some entities that we talk about, I mentioned pods. So the pods can be thought of as a single process running on your cluster. They encapsulate a container or sometimes multiple containers if those containers are tightly coupled. Pod has storage resources, a network identity, and then options about how that container should run. And we'll see that when we get into the deployments and demos. Services. So a service can define a logical set of pods and then a policy to access them. And you'll get more of a sense of that here as we go on. These can also be used to load balance and route requests to multiple replicas of a pod. Deployments, so these describe the desired state of the pods and replica sets. So this deployment definition would say, I want one of these pods always running, or I want 3 of these replicas of this pod always up and available. And the deployment entity is what manages that and makes sure that that state stays the way that it's desired. That if I told it I want 3, it'll maintain 3. And I'll show you a demo of that as well. And then the deployment controller changed the current state to the desired state at a controlled rate. So as pods go down, come up, this deployment controller will manage the number of pods to make sure that they're the way it should be. And then volumes, we aren't going to demo those tonight, but these are links to actual storage. As a container tears down, all of the information in that container goes away. They're designed to be able to be created and destroyed without impact. But in any of these, you're going to want to point to databases or file storage. So the way you do that is through mapped volumes, where these containers will actually map to persistent storage that survives across containers and survives restarts, etc. So how does Azure Kubernetes Service implement the Kubernetes kind of architecture? So it's a turnkey solution for Kubernetes environments. You can imagine we're going through this now. If you're trying to deploy this in your own data center or on-prem, you got to set up the master node, all of your worker nodes, make sure that they're all installed and configured with networking, then all of that access. So AKS takes that away and sets up a lot of that for you. So they basically give you the managed master node. So the API server, database, controller manager, scheduler, AKS, when you create an instance, you get all of that. And then you define the worker nodes. And by worker nodes in AKS, they're just virtual machines. And so you define what virtual machines will be available to run whatever you need to inside your container instance. So it really combines several Azure technologies together to build all these. So virtual machine scale sets, load balancers, and Azure container instances. So as far as scaling, there's multiple levels of scaling in AKS. So there's node scaling. And so this uses the virtual machine scale sets resource inside Azure to dynamically increase the number of nodes. So these are actual virtual machines that, as they become loaded up, the scale set mechanism can actually spin up a new virtual machine that gives you more capacity to run more pods. And then pod scaling uses the horizontal pod autoscaler to dynamically create and destroy pods. So you can have multiple instances of your application running, and it will automatically create and destroy pods based on the required system load. And then there's a concept also in Azure of virtual nodes, and I think it's, why can't I think of the AWS name? It's basically, they take away, you don't have to manage virtual machines. It will automatically spin up enough back-end nodes for whatever instances you're running. So it's kind of nice because you can seed control a little bit and you don't have to manage actual VMs. However, it can be more expensive depending on the type of workload you're running. So my next slide here is pricing. So it's free. Well, not really. They give you the manager. Spinning up an AKS instance is completely free. You don't get charged for any management or controllers or anything like that. But you pay for the virtual machines that serve as nodes. And then the virtual nodes are billed as Azure container instances on a per second basis. So kind of the guidance there is if you've got an app that is always on, the virtual machine standard Kubernetes architecture is likely going to be your best scenario. If you've got a burstable activity that really spins up, does something, and then goes away, the Azure Container Instance virtual nodes may save you money if you can control it that way, if you can set it up. Again, every kind of architectural decision is different and pricing can fluctuate, but that's kind of how they differentiate things between the classic, you manage the virtual machines versus just allowing Azure to manage the virtual nodes. So, all right, so that was my little overview presentation. Let's get to building some stuff here real quick. So just a real quick demo overview. This is a very, very simple and convoluted app, I guess, but it works really well to demonstrate kind of all these things. So we've got two apps here that I'll show you the code for in a second, a main app and a backend. So kind of like a microservice architecture, sort of. The main app, though, just takes in a web request, and it runs kind of an infinite loop for a few seconds just to really load up the processor in the pod And then once that infinite loop completes, it just sends the value to the backend, and the backend just sends it right back and then returns a response to the user. So this is kind of the demo that the main app is going to get hammered really hard and going to have high CPU utilization. The backend is going to have almost nothing. And then on the right here, we'll show kind of the overall architecture. A public IP address will be provided, come in through an Azure load balancer, hit the main app service. This is going to load balance requests across the pods in the main app. The main app, when it gets to this point, is going to make a request to the backend service IP, which is going to load balance request to the backend pods that could be running on multiple nodes in the system. So that's kind of the overview. Let me jump in and I'll share this out. We'll share this all out with just a bunch of resources here and links to different things. So let me jump in. I'm going to jump around a little bit because it takes some time to create the environment. So I'm here in the Azure portal. I've already got a resource group set up, and you'll see I have one resource already set, and that is a container registry. So when I build this app and build these containers, I'm going to put them out in Azure so that their Kubernetes service can actually pull them down and spin those things up. And you'll see how all that works, but I've already gone ahead and created this. So I'm going to add a new resource, Kubernetes service. I don't know why it thinks I'm in East Asia, but we're going to correct that. I'll give it a name here. And then here's where you're going to pick your virtual machine size. I'll show you this. I'll just do show all. And so this is where, by default, it's going to try to create a 3-node cluster. And you can see that you've got a lot of different options for VM sizes. And you can get all the way up to, before I get to my limit, I could spin up a 3-node cluster of 3 machines that are $26.50 per month. So be careful when you're doing this to make sure you pick the right ones and go through this process of maybe not accepting defaults and really thinking about what VM to choose. I'm going to go ahead and just pick the cheapest one I can, 2 virtual CPUs, 4 gigs of RAM, etc. So I'm going to go ahead and just pick the B2S, cheapest one that they've got. And actually, and you'll see why here, I'm going to set this down to actually a 1-node cluster. Go ahead to node pools. We won't get into all of these. You can actually have multiple pools of nodes and set things up so that certain pods get run on certain groups of nodes and other pods go to different pools. So you could have a really cheap pool that the apps really don't need much processing power. You could also have a pool that has really high-end nodes on it if you've got more critical or high-performance workloads. This is where you would set your virtual nodes if you wanted it enabled or disabled. I'm going to leave it disabled because I'm going to use simpler networking. If you enable virtual nodes, you have to use advanced networking, which creates links between your AKS instance and the Azure container instance environment that will dynamically run those workloads. I'm going to leave it disabled, and I'm going to leave my scale sets enabled. Otherwise, we wouldn't be able to scale our nodes. Authentication, you can use service principal or the system assigned managed identity. This managed identity, my understanding, and I'm certainly not an expert on all the permissions and roles within Azure, but this, from my understanding, is kind of a wrapper around the service principal, and it makes things a little bit easier to manage within the AKS environment. So I'm going to go ahead and pick that one. On one of the next screens, I'll show you something that this enables. And we'll just leave the default role-based access control enabled. Networking, I'm going to leave everything as basic. You can have it as a private cluster. You can have network policies that define routing into the environment. You can have application routing, which creates some DNS entries for you. I'm leaving all this off for this demonstration. For this integrations, because I picked managed identity, it's going to let me link to my container registry directly from here. If you pick service principal, this would not be available, and you would have to set up secrets inside your Kubernetes deployment environment in order to be able to hit this registry and pull down images. So I'm sure there are a whole other host of reasons why you would do that. The reason I'm picking it mostly is because this shortcuts this and makes it easier to pull down images. And we'll leave container monitoring on. Tags, can leave that blank. Review and create. And go ahead and create. And this will take a few minutes to actually initialize. So I will jump over to the code, but does anyone have any questions or things they want to jump in here before I jump to the code and building the containers and getting everything deployed? All right, we'll keep rolling. So we're going to jump to Visual Studio Code here. And we'll show you kind of what we've got. So the applications here are just Python Flask web apps. Really, really simple. This is the entire main app. Just importing stuff from Python, using some environment variables. And so this is really the CPU chugger that is built into this. We get the current system time, count up by 50 until we hit that system time. So this does absolutely nothing but just run a long loop. It then passes that current time to the back end, gets it back, and then it just renders it out to the screen. That's it. And then for the back end, another Python Flask app that just takes in a number and spits it right back. That's it. Backend's going to be listening on 5001, and your main app is listening on 5000. So completely just for demo purposes, but you can see how, we'll see when this goes in, if you've got multiple pods communicating with each other, how this works out. The other thing you'll notice in each one of these files here is a Docker file. So this is really the script that will allow me to package that Python app into a Docker container. And so every Docker file starts with a base image. And for this case, I'm going to be running with the Debian Linux stretch version, slimmed down version of the image. So this is going to pull down a version of Linux. And then inside of that container, I'm going to run commands. So I'm going to run an apt-get update, apt-get upgrade, and then I'm going to install Python pip. And then once I've got that installed, I'm going to install my dependencies, Flask and requests. I'm then going to copy that Python file into the container, copy all my templates into the container, and copy my static resources into the container. I'm going to tell it I want to expose port 5000, and then when this container starts up, it's going to run this command, Python3 with the argument main.app.py. So when the container starts up, it's going to start this Python app. So this is kind of the script that will create that Docker container and this whole environment and application. So base Linux environment, a couple packages that are required to run this app. That's it. That's what this container has in it. Same thing for the back end. Very similar. I don't need request on this, so I don't have it, and I don't have any other static files. So I'm just going to copy that Python file into the container, expose 5001, and then run the backend file. So that's really it. That's all it is. So we're going to create these two containers, and I'll show you how to do that. I have got Windows Terminal here. Let me get to my. All right. All right, so let's start with the backend one. So all I'm going to do for this, I've got a Docker file in here, right? So I'm going to do Docker build, I'm going to tag this. And tell it to look in the current directory. So what you'll see here is it's pulling from Docker Hub, actually is where it's the default that it looks at. It pulled that Debian stretch image down, and now it's running all of those scripts inside the container, pulling down Python pip. You'll see it then, it will run the pip command to install Flask here, step 7 of 10. So it's collecting Flask, getting all that, and now it's telling it run the command, and we're done. So that container has been built. And if I do this, Docker images, you'll see this container image was created. So I don't know, that was a pretty simple one. It didn't take much time at all, but let's say it took 20 seconds. What we're going to do is we're going to now build the main. And you see it skipped over downloading the Debian stretch, or it completed almost instantly. And that's because it already had it locally. So what's nice is once you get some of the base images down, the first time you do it, it'll take a while. It's going to download it. If you're building other images based on that same base image, it'll go really, really fast because it's already got that down, and it will pull it from the cache. So now we've got our 2 containers built. Let's look at Kubernetes. I'm going to look in here. So let's go to, these are YAML files that define our Kubernetes deployments. Okay, so this is the definition for a deployment. And so this is going to be the main app. So Python main deployment, you can name this whatever you want. The selector, Python main pod, and then this is the template for the pods that are getting created. And then here's the container spec. And there's a bunch of different options you can put in here. This is kind of a bare minimal sort of thing. But you'll see here, the spec is calling for this image, Johnny Rue's main app latest that we just created. This is the other thing that really impacts the scaling, is the limits and request. So what this is actually doing is I'm setting a limit for these pods that the maximum amount of memory that it can use is 128 megabytes. And it's sort of 128 megabytes. This MI is a power of 2 thing. You can read about that in one of the resources that goes into great detail about actually what this is, but it's about 128 megabytes. And then this is 500 milli-CPU. And what this translates to is half a CPU. So 1 CPU is 1,000 milli-CPU. So 500 is going to request half, or set a limit of half a CPU. And this is consistent. I don't care if you've got a 16-core VM or a single-core VM. This is going to tell it use half of a CPU. And then this request is going to impact the scheduler, and the scheduler is going to look at the available nodes, and this is going to say, for this pod, I want a minimum of 0.4 of a CPU available, or 400 milli-CPU. And the scheduler is going to have to find a node that has that capacity available in order to schedule this pod. And you'll see that in action here once we get to Azure. And then here I'm just defining that this container port is 5,000 on the main app. The next one we have is a service. Again, this is just a kind of wrapper or the load balancer that will point to all of the pods of type Python main pod. So this service, if you make a request from this service, it's going to load balance to all pods of this type. And so these ports here is I'm just using the same one, but you could actually use different ones. I'm routing external port 5000 to the target container port of 5000. And you'll notice here I've set a type of load balancer. VS Code's kind of cool because it'll give you context if you highlight over it. I won't read it, but basically load balancer only works inside cloud environments because what it does is it triggers the cloud environment to actually provision a real load balancer and give you an external IP address that it will route in. Otherwise, you can read your cluster IP, node port, and different ways to define this type of service. But actually, on Windows, if you install Docker, let me open this up here. If you install Docker Desktop, it will also install Kubernetes, a single node Kubernetes cluster. You have the option to enable it or disable it, but you have that enabled here. And it will actually, this type of load balancer, if you run it locally, will create a mapping to localhost. So we've got these individual ones. This file here, this deploy all, is just chained together the deployment and the services for both the main app and the backend app. So let's go ahead and deploy it. The way you do that is the kubectl command. I'll do this. See, I've got a single node here on my Windows machine, just the Docker Desktop app. What I'll do is kubectl apply. So I just applied that file. You'll see created a deployment, created the service, created a deployment for the backend, created a service for the backend. Now, if you run commands like kubectl get deployments, got our 2 deployments. It's got one of one pod ready. Here's our 2 pods running. And you'll see I've got my back end is just a cluster IP load balancer, no public or external IP address because this is inside the cluster on 5001. And then this main service I've got on localhost 5000. So now if I've done everything right, spinny, spinny, spinny. There you go. That's a beautiful app right there. So I will go ahead and I'm going to push these, take the next step. Sorry about jumping around. I'm actually going to come back into Azure now that this resource has been created. And I'm going to do one other thing and show you because this takes a couple seconds and I can have it running in the background. Once you've got your instance set up, if you come here to node pools, remember we set this up with just one? Right now the scale method is set to manual. So I could set this to 5 and click apply and it would go out and try to create another 4 VMs. But what I want is to auto scale this. I'm going to auto scale this with 1 node and a maximum of 3. And I'm just going to go ahead and apply this now. And so this actually takes a little bit to go run. So that's why I jump back here. In the meantime, I'm going to come back here into VS Code and show you that with the Docker extension, here are my 2 Docker images. I'm going to push these up to Azure. So you can do this all through command line, but you can also do it from here. What's interesting is the first part of this is the repository. So I had just tagged it with Johnny Ruse. If I want this to go up to my Azure repository, they give you the URL when you create it. So it's johnnyruse.azurecr containerregistry.io. So I'm going to tag it with that, and that will tell it, push it to this registry. And so this was the back end. So I'll wait till this finishes, and you'll see it's pushing up. It came down to, what, 6 different packages that build up this whole container image. And I'll show you that here in a second. But keep an eye on how long this took. I don't know, another 15, 20 seconds, something like that. I'm going to push the main app now. You see this mounted from backend. So since these are very similar images, same base image, Python apps, etc., it was able to use stuff that it already had in the container registry when we pushed this. So this went a lot faster, and it says it was mounted from that other repository. And if I go to Azure Container Registries, under repositories, you'll see I've got a backend and the main app are here available for me. All right. So now comes the actual good part. We get to run in Azure. So we're going to try this. It was working really well, and then it wasn't. If any of you are familiar with Windows Terminal, new kind of version, you can actually spin up an Azure Cloud Shell right here locally. So let's see if we can get this up. If this doesn't come up, you can always use the embedded Cloud Shell inside the Azure portal. But I'm going to try to see if we can make this work. All right. We're connected. All right, so we've got our Kubernetes cluster up. This is all good. I'll tell you what. Sorry for jumping again. I missed one thing I wanted to show everybody. Remember I talked about auto healing and how deployments work? So I had that deployment that wanted a single main pod and a single backend pod.
I'm going to interrupt. Is this Azure? Is this power? Is this administrator PowerShell instance being run on your desktop, on a Windows computer, in Azure?
Sorry, yeah, so all right, so this is Windows Terminal, and so this is just a local PowerShell window running on my Windows machine.
Okay.
This tab has actually connected me to the Azure Cloud Shell that is configured for Bash. It's the exact same thing as if I came in here and clicked on the Cloud Shell in Azure, which would run inside the browser. This is just a running locally on my machine, but connected to my Azure account.
Thanks.
Does that make sense?
Yep, sure does.
Hey, John, I have another dumb question. With the new Windows
Sure.
terminal, how do you do copy? I mean, how do you do copy if you wanted to copy text in the window? Because I was doing that actually right before this meeting, and you just like that?
Right click everything. So I'm going to go ahead and just, I'm going to delete this pod, but I need this pod name, so I'm going to highlight it. Just left click drag, right click, puts it into on the clipboard, right click again, post it where the cursor is.
Well, that was a lot easier than I thought. Okay, thanks. Sorry.
Yep. I think this has Control C, Control V shortcuts, but I'm so used to doing the right click thing. So anyway, let me go ahead and delete this pod. This only takes a second locally, but what you'll see is, all right, so it deleted that pod ending in J95NW. We'll give this a second, it'll come back. Always takes a second locally to do this. So just keep a note here, 2 pods, both up 5 minutes, 44 seconds, J95NW. All right, wakey, there we go. There you go. So you see, I deleted it and one came right back. So that is that deployment that is monitoring the status, and the deployment says, I want to have at least 1 pod of Python main available. And it went down to 0. So it said, nope, I got to start up a new one. So it automatically started a new one. If you want to delete these pods, you've got to delete the deployment. And then the deployment will tear down all the pods that are tied to it. So that is kind of the self-healing. Same thing would happen if something in this application crashed that caused the container to fail and die. The deployment would spin up a new one almost immediately when it detected that it was kind of out of phase. So wanted to demo that. All right, sorry about the jumping around. Back here in Azure, this is going to look very familiar to what I did locally with my local Kubernetes instance. I'm going to run, let's just take a look, kubectl get nodes. For some, it failed. So this is expected. When you spin up a new cluster, your Cloud Shell doesn't have a connection to it. So you have to run a command, and I'm going to copy and paste it, but I'll give you a ability to look at it here. So standard AZ shell commands, AKS, get credentials, give it the resource group name, and give it the name of your Kubernetes service instance. I've done this before with the same name. So if this likes me, and I know it's going to fail on me, isn't it? It's authentication. There's some authentication issues with the Windows Terminal Cloud shell versus the browser-based one. Yep, you get this error. If you see this, you've got to re-authenticate. Give me 1 second. I'm going to pause because I got to actually type in a password. I'll tell you what. Can everybody see my screen again here? This actually should be fine. If everybody can see my screen again, I resume sharing.
Yep.
When you create a new Azure Cloud Shell window, if you haven't authenticated, and I was, but it got out of whack, so I'm going to re-authenticate. It's going to give you a link to this device logon. And then it gives you this code. And actually, if I've authenticated recently, yeah, okay, good. That's it. All right, signed in, authenticated, and then I'll tell you what resource you want. I want my IA one. Yes, I'll save them, although every time I've saved it and come back in, it blows up. Good stuff. Now let's see if that command now works. If it doesn't, I'm going to run it in the Cloud Shell in the browser. I was really hoping this would work. Yeah, it's going to fail go. This command actually comes back pretty quick. All right, we're going browser-based, guys. There we go. Now it's working. So I've already used this Meetup AKS name before, so it's giving me these options. If this is the first time creating it, you wouldn't see that. But now what you'll see is merged Meetup AKS as current context in .kube config. So now I can run kubectl commands just like I was on my local machine. Good deal. We're up and alive. I took the liberty of already uploading that deployment file here into my Cloud Shell. You can do that via this just upload, download files, or you can open Nano or the embedded text editor here and copy and paste the text. But I've just created this. And then I will show you, before I deploy it, I will do this. So it's kind of the same commands are kind of it's kubectl, kind of verb, noun, and then identifier. So remember I was talking about the request and limits. So you'll see on this first worker node, there are some services already running. And so you see that there are already requests and limits set for some of these other services. So you'll see that each one of my VMs, remember, had 2 CPUs, and you can see that here. So think of that as 2,000 millicPUs. Right now, the request load on this node is 699 millicPUs. So just keep that in mind as we start doing this. So I'm going to go ahead and some opera. And so you'll see this very similar response that we got from locally when we're running on my local machine. Get deployments. There you go. Here's our 2 pods. There you go. So you'll see that Azure spun up, because I've given that load balancer type of the service, Azure actually provisioned a public IP address for me. And so if I go ahead and copy this and replace it there, there you go. So now my app is running in AKS. So you can, the nice thing is, especially on Windows with the Docker desktop, you can test all of that Kubernetes stuff locally with a single node, and then your deployment files should just work once you've pushed them out to Azure. But here's where Azure gets fun, and what I like to refer to as the promise of the cloud, right? Where you can tear down and spin up resources dynamically based on system load. Let's look at that node again. So see, we're now at 1600 millicPU because I've deployed this the back end, which requested 500 millicPU, and then the Python main requested 400. So now I'm at 1600 millicPU request, right? 1599. So there we go. Got these 2 running. What I'm going to do is I'm going to come back to terminal. I'm going to open up a new tab here, and I'm just going to run a real quick script. If I can get my spacing right. Still have it? Yeah, okay, good. So I'm just going to start hitting that service with traffic. There you go. So we're getting responses. I'm going to copy this and open up a new window and run this exact same thing. So he's got two of these that are just infinitely going to try to hit that endpoint. And so now what I can do is you'll start to see, and this is provided by this metrics server add-in that Azure gives you. If you were trying to spin up a Kubernetes cluster on your own, you'd have to manage the installation of all this. But the metrics server is monitoring the utilization of CPU and memory of the pods. And so this top command will show you, and this is kind of a rolling average as stuff starts to hammer this. And what we should see is, as we're running this, I'm going to run one other command in here while this is just hammering. And this is completely not needed, but it helps with the demo. I can show you this. That cluster autoscaler, which was the virtual machine scale set, by default, when a node becomes unneeded, it waits 10 minutes before it actually tears it down. I don't want to wait that long because I want to try to wrap up by 6:45. So I'm going to reconfigure it to set it to 1 minute. Just something I want to do. So this will take a couple seconds, in which time the kind of rolling average on the utilization of those pods should have increased. So I'm expecting to see, because it's running that infinite loop, right? So not truly infinite, but this should actually peg out at 500 millicPUs. It's going to hit its limit, because I got two of these just constantly hammering that endpoint. So this will come back here in just a second. And then just kind of as a preview of what's going to happen is what you should see is this should peg out at 500 millicPU, but you'll still just get these two pods, the back end and the main pod, right? Because we have not enabled pod scaling. And so that will be the next thing that we do once this command comes back. Any questions while this is doing its thing? I expect it to take 30 seconds or something.
Hey, John, just Dale, didn't you
Sure.
Didn't you scale up, make that 1 to 3 or something like that earlier, or is that a different machine?
I did, and yeah. So we'll show that. So that was the virtual machine scale set. So I told it I want a minimum of one. I want a minimum of one actual worker node, but under load you can burst up to 3 worker node instances. And so right now, because I've only got these 2 pods running, I've got enough capacity on one node to run this application. So it'll sit at 1. There we go, it finished. What I'm hoping to demonstrate is that as you start to increase the number of pods and increase the load on that, it will actually, and let me see if I can prove myself right here. There we go. See, this CPU cores is pegged at the limit, 500. You'll see the back end, almost nothing. It's barely using any CPU whatsoever because it's just taking in a value and spitting it right back. So now what I'm going to do is I'm actually going to enable what's called what I mentioned in the PowerPoint is the horizontal pod autoscaler. And so I'm going to point this autoscale. I'm going to tell it to autoscale this deployment. The deployment name is Python main-deployment. The CPU percentages across all pods, if the CPU utilization goes above 50%, create a new one, spin up a new one. And I want a minimum of 1 and a maximum of 5, so you can control this. So I'm going to go ahead and run this. And you'll see the horizontal pod autoscaler auto-scaled. So now I've got this pod running at 100%. And if we give this a second. All right, I got my 2 original, and I've got 2 more, and they're sitting in pending status. What you would expect to see is container creating, where it's pulling down the container image and starting up. But you see them just sitting here, and I can keep doing this. They're just sitting in pending. So let's take a look at one. And since this is the browser one, it's the browser copy paste. So I'm going to describe this pod. And what you'll see here is, warning, I failed to schedule this pod. The scheduler could not find a node with enough CPU to handle that request. So it triggered a scale up. And so this AKS agent pool, so my scale set, has been told to go from 1, it was 1, I want to go to 3. Or sorry, I want to go to 2, I've got a maximum of 3. And so now what we'll see is, and this takes a few seconds, is in the background, it is actually spinning up another instance of a B2S virtual machine. It's setting it up with the appropriate Kubernetes resources, and then it will join it to my cluster. And that can take, it can take a minute or 2. Just to talk about that virtual nodes thing, if you had enabled that and set up advanced networking, when you viewed your nodes, you would see a virtual node along with your standard VM nodes. And you can, I have not dove into this enough, there's certain ways that you can configure things, like I mentioned, for an application that runs perpetually. It probably makes more sense to put it on an actual VM versus paying the per second pricing on the container instances. However, you can set it up to where you could have 1 or 2 pods that are running on standard VMs, but then under heavy load, when you burst, it will actually choose to schedule those additional pods onto the virtual nodes. So you can manage cost that way. That is probably a topic for a whole other presentation. But what you see here now finally is we've got a second VM that has joined our node pool. And now these 2 other pods are pulling down their container images. And in just a second, they're running. So now, when I'm running this this loop to hit the endpoint, Kubernetes will now load balance across these additional pods in that service. So because I'm referencing the service, the request comes into the service, and the service will then knows that I've got 3 pods that match my service definition. I'm going to load balance requests to these pods. All 3 of these pods then are making requests to the backend service. I have not set up the horizontal pod autoscaler for that, but if I look at its utilization, still barely utilized. So even if I set up a scaling on it, it wouldn't create another pod because it's barely getting hit. So now we've seen it scale up, we've got an additional VM. Let's go ahead and stop these. And so completely remove the load from from all this. So at 3 of them, with 2 instances of PowerShell hitting it, they were running at, I don't know, 220, 263, 300 milli-CPU. I think if you average across those, what 50% would be 250, because the request limit was 500. So you're getting real close to needing another one, as that whole group would have been above 50%. And you can actually monitor that. The horizontal pod autoscaler, get HPA. Right now, nothing's hitting it. So I'm at 0% utilization on those pods, and my target is 50%. So min is 1, max is 5. The pod autoscaler has actually, and I think we were above 50%, because it asked for 4. So yeah, so we've got 4 instances of the main pods running. So now that I've removed load completely from this, what we should see, and this is the part that doesn't demo extremely well, this refreshes about every 5 minutes, the horizontal pod autoscaler. And so what you should see is, and we'll just keep monitoring this, and I can open it up for any questions or anything while we're looking at this. What you should see is this scaler will say, all right, I've been below this threshold for long enough. I no longer need 4 replicas. I just need the 1. And then what will happen is it will tear down 3 of these 4 pods. And once that happens, the nodes themselves will realize, hey, I'm no longer needed. The load on the system has dropped down to where this one node can handle all of the available requests on me. And it will actually then tear down this virtual machine. So before, where I said each one of these costs $30 a month, if I had one of these running, that was $30 for that month that this ran the whole time. This is going to be a few cents because it was only needed for a handful of minutes to run that and sustain that load before it tears it back down. So you'll just be billed for however long this VM came up and was alive. Let's see if we've reached our termination point yet. Yeah, this hasn't set up. Like I said, there are ways to deploy this to get the advanced settings of the pod autoscaler and set it to not wait 5 minutes, wait 30 seconds, set different things up. But I just didn't do that in this demo. So anyway, hopefully this will kick in here. Hopefully this was helpful. I'm pretty fast moving through a lot of different things. We'll make sure we get with Mark to share this presentation out, because all of the links and URLs on the resources page will allow you to really dive deep into all of these concepts, all of these different things about Kubernetes, about AKS, how it all works. But hopefully this demo kind of showed with AKS how you can deploy a containerized application and then automatically scale it to hopefully provide a good product. We'll keep an eye on this, but if anyone has wants to jump in, any questions, want me to show anything else, definitely happy to.
Very cool, John. Have you worked with any other Kubernetes or container services, whether it be on AWS or any other cloud platform?
I have not. The name just popped into my head. AWS Fargate, I believe, is their competitor to virtual nodes, where you don't manage virtual machines, or I guess in their case, like EC2 instances. You would just deploy containers and it would deploy them magically to whatever resources it has on the back end. I think the same limitation comes with that is can be more expensive than managing the EC2 instances themselves. But I have not deployed container systems or used AWS Kubernetes Service or Google Cloud Kubernetes Service. I've really just experimented and played around with AKS. But I know I will say that I mentioned this other container orchestration, Docker Compose, Docker Swarm. I think at one point Azure had Docker Swarm support, and that has been discontinued and shut down. Kubernetes has kind of become the de facto standard that all the cloud platforms are implementing.
So John, how do you, I mean, there's a lot of consideration on, whether to use this distributed system or not. How do you, what are the, not really rules, but how do you determine whether you need it or not? I mean, at what point, is it load or speed, the ability to ramp up? How do you come up with a decision to make whether to use Kubernetes or not? Because it seems like there's a steep learning curve, and what are you trying to gain from it? I know that's a kind of a loaded question. I'm just trying to understand from a high level what determines whether you should use this technology or not.
Yeah, and I guess it really boils down to, are you looking at the type of application? Are you looking at a monolithic application versus microservice type architecture? So you're absolutely right. A monolithic application is probably much easier, straightforward, less of a learning curve than some of this microservice architecture type style. The downside of that is really scalability, portability, etc., and the granularity at which you can scale, right? If you've got a huge monolithic web app and it starts to get hammered, you can spin up another instance of that web app and load balance between them. But you got to spin up the whole thing if it's a self-contained kind of monolith. Whereas with Kubernetes or microservice architecture, if I've got one service or one piece of an overall web app or one API area that gets a ton of traffic, I can scale that piece up and leave some of the other ones at a lower resource availability. So there is no one answer of, if this, go microservice Kubernetes. If this, go monolithic. Every application, every project is going to have its own challenges and own architecture designs. And then once you decide to go microservices, how granular do you get? We're facing that issue right now with the current client of trying to determine how granular to break it up. Because we're definitely doing microservices, definitely going to go Kubernetes, but if I'm managing vendors and, vendors and payments and different things, does each one of those become its own service? Or do you have a accounts payable service that contains vendors and payments, et cetera, and that's its service? So
right, because
kind of an answer, non-answer.
Right. Yeah, trying to draw that line is kind of hard because I guess as you scale out, you have to shift and adjust as needed, whether it's beneficial to doing or not, because I can, just see spinning up, hundreds or thousands of these things, as it keeps growing, and then you wind up with not really a maintenance nightmare, but it seems like it's a lot to manage,
Yeah, that's why, I mean, a container orchestrator like this is absolutely critical, because there's no way for you to monitor, hundreds, thousands of these, whatever. Whereas Kubernetes could do that. If I need 100, it can spin up 100 and tear down 50 of them and manage all of that. Mm-hmm. But you're right. I think it's kind of like a DevOps CI/CD stuff, right?
Right.
it's a pain sometimes to set it up, but once you do and you've got it to where as soon as I check in code, it builds, run tests, and deploys, it's beautiful. Kubernetes, I think, is kind of the same way. There's so many ways to set it up and so many things to do and boxes to check and make sure it's configured just right. But once it's configured and set up and working, it kind of manages itself, and you deploy containers and it just will scale up, scale down, turn things on, turn things off. Have I gotten a deployment to that state yet? No. But it's a work in progress.
John, question. So one of the pods, like one of the nodes, I don't know which one is the right word, has to run on normal traffic, right? Like or is there a way, you could say you don't have any traffic, right, coming in? So, something like serverless architecture. Is it a way to say, oh, don't write anything, don't spin anything up, or don't incur any computational or something resource to kind of save money? Is that possible to even to go below, I don't know, one instance of it running?
Even below, so it would spin up a VM, and I think really the win is the serverless, because I'm not aware of that. Kind of spinning this up, the idea is that you've always got like something running, right? And a lot of times what you'll see is in like a production deployment, both the Python main and the Python backend would have like defined that I want 3 of these running at all times across 3 nodes, right? So that you could have a pod failure and the application still runs. You could have a actually physical hardware or a VM failure and everything still runs fine because you've split them out, and then you can burst above that. I don't know. That would be an interesting question to see. Can you completely have a clean slate and then something triggers the creation of a node and a pod? But I believe, at least in this architecture, with the VMs, with a virtual machine scale set, you've got to have one running and then can burst up to however many nodes. And then on the virtual nodes, certainly the pods will burst and you pay per second pricing on that. But I'm not sure how you would, I'm not saying you can't, is to have like 0 pods and then scale up to 1 once an event happens. It's usually you have 1 pod, and then as that one gets overloaded, it'll spin up more. Does that answer your question?
Yes, it does. Thank you.
Yes, no, maybe. Just FYI, if you still see my screen, you can see we're back down to 2 pods and 1 node. So it tore everything back down.
Got a couple of questions in the chat, John.
Yeah.
Microservices. Are there other apps that are good candidates for AKS?
Other apps. Stop showing me into the password. Sorry, I pulled up the chat too, and I'm reading ahead and getting distracted. What kind of apps are good candidates for AKS? So really it's the microservices is where AKS really comes in. When you've got containerized apps. Frankly, you could, and in some Microsoft documentation, they have shown that you can containerize a monolith. So you may not have an application broken down into 100 different little pieces, but you just have one application that you containerize it. You absolutely then could run that on AKS and take advantage of the auto scaling, load balancing, etc. you'd have to manage and make sure that the containers themselves can start up quickly and that they don't get so large and so big that the auto scale up, auto scale down really doesn't buy you anything, or takes so long to adjust that it doesn't give you that benefit of bursting. The idea of containerization is to try to keep things small so that startup is extremely fast for when those containers come up. The slowest part of all of this was spinning up the new node and actually getting that virtual machine provisioned and up to where it could accept the pods. Once it's up, it takes a few seconds for containers to get created on it. But absolutely leveraging some of if you're already deploying an application to a virtual machine, it's a web app of some kind, hosting it in AKS and applying some of the auto scaling features could absolutely work for you. Can we have spot VMs for AKS? Spot VMs, I know the term, and it's been a while since I've played with it. I don't know the answer to that. Kana, is that how you say it? Sorry if I butchered the name. External monitoring, Splunk, Prometheus, which is good. Where do we upload your recording? The recording upload is from Mark. I don't know where that is. Splunk, Prometheus, I have not. I will tell you though, I just found earlier this afternoon, I rebooted my PC, but let's see if I have it. I just stumbled upon this GitHub sample, which is the autoscaling with the virtual nodes, which I want to get into, and this includes Prometheus and other monitoring that I have not played with. So I was anxious in some additional free time coming up to look into this demo and play with things like Prometheus and Splunk. So, nope. And then another question, how good to deploy on existing KDS clusters and spinning up new clusters for each application or for SEC? In my opinion, I would have as few clusters as possible and manage the number of nodes, just an overhead management. However, I guess it depends on the relationship between applications, right? If they are wildly different, completely different, I guess, intents for the apps, maybe it makes sense to have a KDS cluster for this environment versus another environment. But I know at the client, we are having this discussion now at the current client. We're going through a lot of effort to set up a on-prem or in their private cloud Kubernetes cluster, much more difficult than what I just showed you here with Azure doing a lot of the management for you. But I think the push and the discussion there is, if we go through all this trouble to set up this cluster, let's make it available for not only the application that we're working on, but other teams working on apps to deploy their services and pods and containers too, versus trying to manage two Kubernetes environments with ingress controllers and API and metrics and all the stuff that you would have to set up manually. AKS makes that a lot easier, so maybe it's a little bit easier decision, or a little bit easier to, if you want a completely separate AKS instance, to do that in a cloud technology. But if you're trying to set one up from scratch, I would set it up really, really well, and then allow it to be used for everyone. And maybe you've got a dev cluster and a prod cluster, but setting up specific clusters per application, just the risk management headache. The good is, I don't know, if a cluster or something goes down, you only lose one app. But hopefully, with the way it's designed with multiple nodes, you wouldn't lose all of your nodes. If you've lost all nodes, then you've got a bigger problem. But the idea that if one of the nodes fails, if you've got things scaled out with the replica sets appropriately, you can actually tolerate a hardware or an actual node failure, and the end user doesn't see any downtime at all.
So you had mentioned you were working on this before with a client. What does that transition look like? I mean, is it a big time effort to go to this new model?
Yeah. So the background of the project is converting a legacy monolith, basically VB6 app, to a modern web app, Angular front end, REST APIs, and the REST APIs we're microservicing them. So they do have, the way their REST APIs are set up, they've got vastly different utilization depending on what service you're calling. So we're splitting this up, and then that's where we're taking advantage of the Kubernetes scaling, so that some of these that get hammered get scaled up more, and some of the other ones we can run still in high availability with multiple pods, but don't need a lot of them. But if they ever do come under fire from a large burst in traffic, legitimate traffic, it will be able to scale out and handle that. Definitely I wish they were an Azure shop, but they have made an investment in a virtual private cloud at one of the local hosting providers. So we're having to provision the actual VMs and then set up the Kubernetes infrastructure from scratch. There are some utilities. KubeSpray is one of them. I forget some of the other ones that leverage things like Ansible scripts and sets of Ansible utilities to spin up a cluster. There's still a lot of management and a lot of things that you have to get right to spin it up. And the beauty of the cloud provider like an Azure or Google Cloud Platform or AWS, any of them, is they've abstracted a lot of that away from you. So that's the challenge, is just getting a self-built cluster set up right with the same level of reliability and resiliency that you would get built in from a cloud provider.
Nice, thanks. Anyone have any other questions? Well, if not, thank you, John. That was awesome. A lot of good information in a short amount of time, and a very nice intro to some very cool technology. So thank you all for joining us tonight. It was a lot of fun. Like I say, I will follow up probably either later on tonight or in the morning with both the recording as well as John's slides. And then within the next few days, we'll have some information about next month's talk, which I hope you all can join us for. Outside of that, I hope everybody's staying safe, and all this work from home isn't driving you crazy. So everybody have a good weekend, and we'll talk to you all soon. Thanks.
Thanks,
Thanks, everybody.
Thanks, John.
Good job.
Thank you.
Good job, John.
Bye. Thank you, John.